Now, because direct computation of these Taylor and Maclaurin coefficients can be tedious, the easiest way to find a Taylor or Maclaurin series is to develop that series. So you want to develop that power series using known series, and you do that with operations such as addition, subtraction, multiplication, division, integration, differentiation, or composition. These are the power series for these elementary functions. So if you had this function 1 over x, this would actually be the series for that function. It would be the sum from n equal 0 to infinity of negative 1 to the n times x minus 1 to the n. Notice that this guy here is centered at x equal 1. If you had the function 1 over 1 plus x, this is your series right here. It's the sum from n equal 0 to infinity of negative 1 to the n times x to the n. If you wanted the series for the natural log of x, it's this guy right here. It's the sum from n equal 1 to infinity of negative 1 to the n minus 1 times x minus 1 to the n all over n. Notice that this counter starts at 1 because we have an n in the denominator, so we can't start at 0. And just like the first one we looked at, this guy here is centered at x equal 1. So everything else, if you just have an x, is going to be just centered at 0. E to the x, its series is this guy right here, the sum from n equals 0 to infinity of x to the n over n factorial. For the sine of x, it's this guy, the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. For cosine of x, it's this, the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. For inverse tangent, it's this, the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1. And then the last one, for the inverse sine, we're looking at this, which is the sum from n equals 0 to infinity of 2n factorial over 2n times n factorial squared, and then times x to the 2n plus 1 in the numerator and times 2n plus 1 in the denominator. Now you don't have to have these yellow series memorized. This would be given to you. The other thing that you see over here is the interval of convergence. So where does this series look like 1 over x? From 0 to 2. Where does this series look like 1 over 1 plus x? From negative 1 to 1, etc. for each one of these. The last one is the binomial series. This guy here is your binomial series, and we're going to talk more about that later in the last few examples. So what we're going to do is we're going to be looking at creating a Taylor or Maclaurin polynomial. Now when we're creating it from these series that are known, it has to be centered at the same place. So I can't use this formula here for the problem that we just had because this is centered at 0 and we were centered at pi over 4, so we wouldn't get the exact same answer. So notice that this guy here would be nowhere near what we have for the other one, which is that for the sine of x centered at 0, it's the sum from n equal 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. So notice these don't look anything alike, but if you do have something that's sine and centered at 0, you could use that formula. So you can only use these formulas if you're centered at the same thing that these formulas are centered at. And we're going to concentrate on using addition, subtraction, and then we've already done integration and differentiation if you go back to section 9.9, and then composition. So we're really going to concentrate on those. Multiplication and division are really difficult because basically what you need to do is multiply the terms in these polynomials. So if I wanted to figure out what is e to the x times the sine of x, what's this guy times that guy? I would have to multiply this guy here, this 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. Multiply that by this guy here. x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I'm just going to put plus dot dot dot. And you'd really have to use the distributive property, and it would get really, really messy. For division, you'd be doing long division of polynomials, so those get really, really messy. So we're going to avoid doing those two, but we're going to be using, again, like I said, composition, addition, and subtraction. Now we are going to do multiplication and division in here, but we're only going to be doing multiplication and division if we're multiplying or dividing by a power of x, not by a series. So let's look at finding the Maclaurin series for the function, and we're going to use the table of power series for elementary functions to do that. Now, on an exam, if you see the directions, or in WebAssign, if you see the directions, find the Maclaurin series for the function, use the table of power series for elementary functions, so that's what you're using to do it. You're going to be using this table right here to come up with your series. On an exam, this table would be provided for you. So let's look at the first one, example 4, which I'm letting you know is example 1 again. So it wants us to find f of x equals e to the negative 3x. So the skeleton function there, or the one that we're going to use, is just f of x equals e to the x, because e to the negative 3x is just a composite function of e to the x. And I know what e to the x is. If you come back here, it's this series right here. E to the x is the series, the sum from n equal 0 to infinity of x to the n over n factorial. So what we're going to do is find our given one here, which is this e to the negative 3x. So for e to the negative 3x, what we'd need to do is, instead of writing the x in our series, we'd write negative 3x. So then this becomes negative 3x raised to the nth power all over n factorial. So all we did there was composition. So we composed e to the x as e to the negative 3x. Well, if we were to expand that out, we could say, okay, well, this is just equal to the sum from n equals 0 to infinity of negative 1 to the n, 3 to the n, x to the n, all over n factorial. And if you look at example 1, that's exactly what we got. Negative 1 to the n, 3 to the n, x to the n, all over n factorial. Let's look at number 5. It wants us to find f of x equals e to the negative 3x over x squared, again using that table of power series for elementary functions. So I already know what this guy is, because this is basically example 4. We know that e to the negative 3x was this guy. It was the sum from n equals 0 to infinity of negative 1 to the n times 3 to the n times x to the n all over n factorial. And remember, you'd build that off of e to the x. But that's not what I want. I want e to the negative 3x divided by x squared. Notice that that is just a power of x. So if I'm dividing this guy by x squared, I'm dividing in here by x squared. So then the only thing that I am left to do here is combine those two. So if I have x to the n divided by x squared, when the base is the same and you're dividing, you just subtract your exponents. That becomes negative 1 to the n times 3 to the n times x to the n minus 2 all over n factorial. This is the power series that mimics this function. What about x cubed times the cosine of x? Well, this again is a power of x. So let's figure out what the power series is for the cosine of x. Well, the cosine of x, if I scroll back up, I know it's going to equal the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. So we say that this is just the sum from n equal 0 to infinity of, again, negative 1 to the n times x to the 2n all over 2n factorial. Now, we don't want the cosine of x, because that's not what I'm given. The given function is cosine of x times x cubed. So all I have to do is multiply this guy here by x cubed, and then this guy here by x cubed. Well, if I do that, x cubed cosine of x is going to equal the sum from n equals 0 to infinity of negative 1 to the n, and then here my bases are the same, they're both x, and I'm multiplying, so I know I need to add those exponents, and that becomes x to the 2n plus 3 all over 2n factorial. Let's look at example 7. F of x equals sine squared x. Now sometimes, and I'm going to do something that's wrong, some students want to say, oh, well, that's easy. This is just the sine of x times the sine of x. And they think they can look up and say, well, the sine of x, and again, all this is wrong, and I'm going to erase it, so please don't copy it down, is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. And they think that they can either square this, so they try to square this, which you cannot do, or they say, well, I can just take it and I can multiply it by another one because it's just going to be that guy times itself. But again, this doesn't work either, because when you multiply series, you can't multiply series like that. What you would have to do if you were doing multiplication of series is you would have to say, okay, well, what is the sine of x equal to? It's equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And then if you wanted to square it, you'd have to take this guy and multiply it by itself, and that would be x, and then x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And really it would be, we would multiply x times x, and that would be x squared, and then this is x to the 4th over 3 factorial, and then that's going to be plus x to the 6th over 5 factorial, and you keep going, then you multiply that one to each one of those, and it gets really complex and really long. So if we can avoid multiplication or division of series, we do. And here we can. Alright, so now I'm going to do it the right way, so you want to start copying down. How would I handle this? Well, I told you, don't multiply, so think to yourself, how do I get sine squared of x to be easier? If you go back to integration, we said, what do? We use the power reduction formula. We know that this guy here is equivalent to 1 minus the cosine of 2x all over 2, or we could write it as 1/2 minus 1/2 cosine of 2x. Well, this is perfect because then this is just a number, this is a minus sign, and this is just a constant multiplier, and this here would just be composition, because instead of the cosine of x, I'd need the cosine of 2x. So I've made myself into something simpler so I can use the power series for elementary functions. So we know again that the cosine of x, just by itself, is this guy. It's the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. But I don't have the cosine of x, I have the cosine of 2x. So let's do that composition. The cosine of 2x would equal negative 1 to the n, and instead of x I write 2x to the 2n all over 2n factorial. And I'm going to leave it there. I'm not going to clean that guy up, so I'm not going to write it as 2 to the 2n times x to the 2n. But that's really not what I have. I still need to take that guy and multiply it by negative 1/2, and then put a positive 1/2 in front of it. So let's write it this way. Sine squared of x, which is 1/2 minus 1 over 2 cosine of 2x, is going to equal 1/2 minus 1/2, and then instead of this guy, I'm going to write our series, and that series was the sum from n equals 0 to infinity of negative 1 to the n times 2x to the 2n all over 2n factorial. So this is the power series that represents sine squared of x.